As we have already noted, in a transient analysis, it is mandatory to specify the starting conditions. There are many different ways in a SEEP-W analysis or in a GeoStudio analysis more generally to get the starting pore pressure conditions. We are going to highlight two procedures here, although there are more. One of the simplest is to define what we call a water table. And so you, as the user, you define the position of a water table, and then based on hydrostatic conditions we compute the pore pressure within each element based on a hydrostatic assumption of the pore water pressure being positive under the water table. Above the water table, we go hydrostatically negative, we make the pore pressure negative, up to some user-specified height here, and the user-specified height, and thereafter we keep the pore pressure constant above this level. There is field evidence and other analysis evidence to suggest that this is somewhat realistic of actual field conditions. Seldom does the pore pressure go hydrostatically negative all the way to the surface. So, based on field measurements, we have our capillary zone, and above the capillary zone, field evidence suggests that we should keep the pore pressure at some constant negative value. So you, as the user, you must specify the water table, and then you can specify the height at which the pore pressure remains negative above the water table. Or in other words, this allows you to define the height of the capillary zone. So that's one way of defining initial conditions, and is actually done quite commonly and quite frequently. Another way to get the initial conditions for a transient analysis is to get them from another simulation. And so we may have done a previous steady-state analysis using SEEP-W, and then we used the steady-state analysis from a SEEP-W analysis in a transient, or to start the transient analysis. Now, the initial conditions could also come from a sigma W analysis or a quake W analysis, but for our discussion here, we will assume that the initial conditions come from another SEEP-W type of an analysis, and we will show you how to flag and tell SEEP-W where is the file and where is the previous analysis that gives you the initial conditions. Let's talk then about time-stepping sequences. Many transient seepage processes follow an exponential form. That is, the process is fast at first, but then slows down with time. A typical example is a consolidation test. We take readings at very small delta t's to start, and then after some time, the time between readings is very long. Unfortunately, in SEEP-W, there are no firm rules to help you in defining a time-stepping sequence. It's often a try and see process, and more difficult, or unfortunately, time steps that are too small give numerical noise. Time steps that are too big give wrong solutions. And so it is kind of a try and see approach many times to get a proper time stepping sequence. We can get some guidance from consolidation theory. If we had a soil sample here, and these were elements, and there was a sudden change in pore pressure, or change in boundary condition, or change in loading, then the first element at the top here should have some significant consolidation. In other words, the delta T should be such that there is in the first element some significant dissipation of excess pore pressures. If the delta T is too small and there is virtually no change in the first element on the surface, so to speak, then we can get some numerical noise and some irregularities in the pore pressure distribution. So we can use consolidation theory to take a look at what might be an appropriate delta T. And if we make the assumption that we would like to look at the change in pore pressure with about 35% consolidation in the first element, and if we go back to the theory of consolidation in most textbooks, we have what is known as a time factor, and a time factor for 35% consolidation is around 0.1. Now you may recall from your consolidation theory that the delta T is related by this equation, where this is the well-known time factor. This is M sub V, a soil property. This is the saturated conductivity, also a soil property. And then we have some area term here, or in other words, if it was vertical flow, it would be the thickness of the element or the thickness of the sample, so to speak. Now, if we were to substitute into this equation a time factor of 0.1, and the unit weight of water is 10 kilonewtons per meter cubed, then this equation reduces to approximately m sub v over k sat times L squared. So although this is a rough estimate of a starting time, it does help in getting So this equation gives us an opportunity to make a rough estimate of a starting time, where L is the thickness of the element. Even more simply, a very rough estimate can be made from m sub v divided by k sat. This sometimes puts us in the right order of magnitude, but it is useful to make initial guess. In the end, the initial guess that we get from this equation needs to be refined by making various runs. So the important point here is that appropriate temporal integration or size of time step is related to the material property, which is m sub v and k sat, and it is related to element size, which comes into here. So to repeat and summarize, obtaining an appropriate starting delta T takes a little bit of trial and error, but this equation from consolidation can help us at least get into the right ballpark to get a starting delta T, but then we have to try various delta T sequences and look at the solution. The important thing is we get irregular results and unreasonable results sometimes if delta T should get too small. So we cannot say, I will make delta T infinitely small and get the best solution. Unfortunately, that doesn't work. Also, we cannot make delta T too large, because in a nonlinear process we need to step along the nonlinear process in appropriate delta T's. We can't step from one end to the next. That will give us the wrong solution. Just a few comments about transient boundary conditions. As we have noted several times, in a steady state analysis our boundary conditions are constant. In a transient analysis our boundary conditions can be a function. And for example, we might make head a function of time, or we have a certain infiltration rate versus time. And we will demonstrate how to use a boundary function in the example that we are going to go through here in just a few moments.